Hello. In this example, we're going to find the arc length parameter at t equals 0. Then we're going to find the length of the indicated portion of our vector r. So we're given our r position vector, e to the t cosine t times the vector I plus e to the t sine t times the vector j plus e to the t times the vector k. And we're considering t along the distance from negative ln4 to 0. In order to do this, we're going to determine s. We're going to use the formula 0 to t times the magnitude of the velocity vector with regard to tau, integrated with respect to tau. So for our first step, we're going to go ahead and find the velocity vector, which is taking the derivative of each of these components. When we find the derivative of e to the t times cosine t, as well as e to the t times sine t, we have to use the product rule. And then, of course, we know the derivative of e to the t is just e to the t. So for my first component, I have e to the t times the derivative of cosine, which is negative sine t plus cosine t times e to the t. That would be I, plus, so our derivative here, again using the product rule, we're going to get e to the t cosine t plus sine t times e to the t, and that would be j, plus the derivative of e to the t is e to the t, k. All right, so now we have our velocity vector. We need to find the magnitude of the velocity vector. So the magnitude of v is the square root of my x component squared. So negative e to the t sine t plus e to the t cosine t, quantity squared, plus my y component, and that would be e to the t cosine t plus e to the t sine t squared, and then plus my z component, e to the t squared. So at this point, this algebra should be pretty simple to you, but we're going to have some foiling. These are almost the same, but you'll notice that sine on e to the t sine t is going to be different. So we're going to have some canceling. So this leaves me with e to the 2t cosine squared t minus 2e to the 2t cosine t sine t plus e to the 2t sine squared t. So that's what I get for foiling this first part. I get something very similar, but with all positive signs when I foil the second. So I'm going to write that out. I've got plus, I'll continue below because it will help me add them, e to the 2t cosine squared t plus 2e to the 2t cosine t sine t plus e to the 2t sine squared t plus e to the 2t. So hopefully we notice those middle two terms cancel, and I can add my sine squared and cosine squared terms. So now I have the square root of 2e to the 2t cosine squared t plus 2e to the 2t sine squared t plus e to the 2t. At this point, we should notice that all three of my terms have an e to the 2t. So this gives me, I'm going to factor that out. I've got the square root of e to the 2t, and under my radical, I'm left with 2 cosine squared t plus 2 sine squared t plus 1. When I factored that GCF out, this became a 1. Square root of something that is squared, that's going to give me e to the t. Over here, from those first two, I'll factor out a 2. I'm left with cosine squared t plus sine squared t, and then I have this plus 1. Of course, we know this value is equal to 1. So I have e to the t square root of 2 times 1 plus 1, or e to the t root 3. So the magnitude of the velocity vector v of t is root 3 times e to the t. Now, we're not done with the problem. I did a lot of algebra there for you. But if we go back up to the top and think about what we know we needed to calculate, we need to find s. So I'm just going to substitute tau in for t. And the reason I'm doing that, the reason I'm using tau, is because I already have a t in my bounds, and I can't substitute a t into a t. So we're just using this intermediate variable to help us. So what we know is that s is the integral from 0 to t of the magnitude of v of tau, integrated with respect to tau in this case. I have the integral from 0 to t of root 3 e to the tau d tau. Pull that root 3 out front. The integral of e to the tau is e to the tau. We need to evaluate that from t to 0. So that is root 3, plugging t in for tau, I get e to the t minus e to the 0. And we all know that e to the 0 is equal to 1. So this represents s. So this gives us our distance or length along the curve. And remember now, we wanted to find that length from t equals negative natural log of 4 to t equals 0. And so that distance traveled is going to be s of 0 minus s of negative natural log of 4, which I'll pull that root 3 out in front, and I end up with e to the 0 minus 1 minus e to the negative natural log of 4 minus 1. E to the 0 is 1. 1 minus 1 is going to go away. I'll go ahead and pull that negative in front of my root 3. So I have negative root 3. And I'm left with e to the negative natural log of 4 minus 1. So we need to simplify negative natural log of 4. That's a negative 1 in front of the natural log. So that's the same as e to the natural log of 4 to the negative 1 minus 1. And I end up with 4 to the negative 1 minus 1, or 1/4 minus 1. So 1/4 minus 1 is negative 3/4. So I end up with positive 3 root 3 over 4. And 3 root 3 over 4 is the length on our curve, on our position vector, from t equals negative natural log of 4 to t equals 0.